You feel it, don't you? That familiar, life-giving warmth on your skin? That blinding, golden orb searing through our atmosphere? Our sun, a colossal fusion engine. Its core, a raging furnace where hydrogen atoms crush into helium, unleashing the very light that paints our world, sustains our lives, and defines our cosmic neighborhood. It's the ultimate star, a beacon of predictable thermonuclear fury. But what if I told you that the universe harbors an entirely different breed of star, an impossible, chilling concept that shatters everything you thought you knew about cosmic fire? Imagine a sun so massive it dwarfs our own, yet radiates no heat, no visible light, a silent, colossal shadow, burning not with nuclear fusion, but with annihilation itself. These are the theoretical dark matter stars, ghost engines of the early cosmos, fueled by the universe's most elusive substance, hiding in plain sight. They are the ultimate cosmic paradox, potentially the true architects of galactic evolution, and they may still be lurking, cold and invisible, at the heart of every galaxy, including our own. The stage for these impossible stars was set in the universe's earliest, most violent moments. For billions of years, cosmologists believed they had the blueprint for cosmic evolution locked down. Ordinary matter, stars, galaxies, all built from the stuff we can see, touch, and measure. But then, the universe screamed a different truth. Galaxies spun too fast. Cosmic structures clung together with impossible gravitational glue. A silent, unseen puppeteer was at work, bending space-time, shaping the very fabric of the cosmos, yet refusing to reveal itself. We call it dark matter. It's the ultimate cosmic enigma, a phantom presence that outweighs all visible matter 5 to 1. It doesn't absorb, reflect, or emit light. It doesn't interact with us, our telescopes, or any of our instruments through any force we understand, save one: gravity. This invisible hand grips galaxies, preventing them from ripping themselves apart, sculpting the vast cosmic web, yet remaining stubbornly, infuriatingly hidden. For decades, it was simply a gravitational ghost, a mathematical placeholder for missing mass. But what if dark matter isn't just a passive, unseen scaffolding? What if, in the brutal crucible of the early universe, this elusive substance ignited a cosmic revolution, giving birth to a class of stars unlike anything we've ever conceived? Imagine the infant cosmos, a chaotic, turbulent maelstrom of hydrogen, helium, and a vast, pervasive sea of this silent dark matter. Clouds of primordial gas, light years across, began to collapse under their own immense gravity. This was the birth cry of the first stars, colossal titans that blazed with furious fusion. But in the densest cores of these collapsing gas clouds, something far stranger might have unfolded. Something that rewrites the very genesis of cosmic light and heat. Something that proves the universe is infinitely more inventive and terrifying than we could have ever dared to imagine. Here's where the universe leans into its most bizarre possibilities, where the lines between science and a fever dream blur. For a star to ignite, it needs immense pressure and heat to force atomic nuclei to fuse. That's the sun's secret, a thermonuclear forge. But a dark star? It laughs at fusion. Its internal engine runs on something far more primal, far more chilling: annihilation. Picture a colossal cloud of primordial hydrogen and helium, hundreds of times the mass of our sun, collapsing under its own gravity in the early universe. This isn't unusual, but now, inject that cloud with a significant dose of dark matter, specifically a type known as WIMPs, weakly interacting massive particles. As this gargantuan cloud crunches down, the ordinary gas heats up, but the dark matter particles, too, are forced into an ever-tightening embrace. They are their own worst enemies. When two WIMPs collide in this super-dense core, they don't just bounce off each other, they annihilate. They explode. Their mass vanishes, instantly converting into pure energy, precisely as Einstein's terrifying EMC2 dictates. This isn't a slow burn. This is a continuous, self-sustaining cosmic explosion at the heart of the star, imagine a perpetual silent bomb. The energy unleashed by these annihilating dark particles blasts outward, heating the surrounding hydrogen gas. This heat prevents the gas from collapsing further, reaching the extreme temperatures needed for nuclear fusion. It's a delicate, terrifying balance. The dark matter annihilation acts as a cosmic thermostat, maintaining an equilibrium where the star is hot enough to resist further collapse, but never hot enough to ignite fusion. It's a star that refuses to become a star in the traditional sense. So, what does this ghostly furnace look like? Not the blazing yellow sun, you know. A dark star would be a truly alien beast. Calculations predict they would be enormous, potentially hundreds or even thousands of times the diameter of our sun, yet their surface temperatures would be chillingly low, perhaps only a few thousand degrees Kelvin. They wouldn't blaze with visible light. Instead, they would be incredibly dim, radiating mostly in the infrared spectrum, like a colossal cosmic heat lamp. They would be cold, diffuse giants, almost perfectly transparent to ordinary light, making them nearly invisible. To our most powerful telescopes, imagine a giant translucent soap bubble stretching across millions of kilometers, its heart a quiet, continuous inferno of pure annihilation. This isn't just theoretical musing, it's a terrifyingly elegant solution to a cosmic problem. If you're captivated by the universe's most profound secrets, by the unseen forces that sculpt reality, then smash that like button and subscribe. You don't want to miss what else the cosmos is hiding. The implications of these bizarre, invisible suns ripple across cosmic history, potentially rewriting the very genesis of structure in our universe. If dark stars truly existed, they weren't just cosmic oddities. They were architects. They were the universe's first, most profound secret. Traditional cosmology posits that the first stars, formed from primordial hydrogen and helium, were massive, short-lived giants that quickly burned out, leaving behind black holes. These stellar black holes then merged and gorged themselves on gas, slowly growing into the supermassive monsters we see at the hearts of galaxies today. But this picture has a gaping, terrifying flaw. We've found supermassive black holes in the early universe that are far too large, far too mature to have formed through this slow, patient process. They appear almost instantly, like cosmic titans bursting fully formed from the void. Enter the dark star. Imagine a dark star, not just hundreds, but perhaps hundreds of thousands of times the mass of our sun. Such a colossal object, sustained by the relentless annihilation of dark matter in its core, could live for millions or even billions of years. But eventually, even the most robust fuel supply runs dry. As the dark matter particles in its core dwindle, the annihilation rate drops, the cosmic thermostat breaks. Without that internal heat source, the immense gravitational pressure of the star's ordinary hydrogen gas would finally, catastrophically, win. The dark star would implode. It wouldn't explode like a supernova. It would collapse inward with terrifying efficiency, bypassing the fusion stage entirely. It would skip the stellar life cycle and plunge directly into a gravitational abyss, forming a black hole that is hundreds of thousands, or even millions, of times the mass of our sun. Instantly, a cosmic shortcut. This isn't just a bigger black hole, it's a seed, a primordial, supermassive seed planted directly into the heart of the nascent galaxy. These dark star remnants could be the true progenitors of the supermassive black holes that anchor every galaxy we observe, including our own Milky Way. They explain how these gravitational behemoths could emerge so quickly in the young universe without requiring eons of slow, painstaking growth. They weren't just the first stars, they were the first black hole factories, churning out the gravitational anchors around which galaxies would later coalesce and spin. But the story doesn't end in the distant past. What if some dark stars never ran out of fuel? What if in the densest, most dark matter-rich regions of the cosmos, these ghostly giants still exist? They would be colossal, frigid, and virtually invisible, perhaps lurking in the halos of galaxies, or even in the very hearts of galactic clusters, their annihilation engines humming silently, perpetually. They could be the universe's ultimate hidden objects, shaping galactic dynamics, influencing star formation, yet forever beyond the reach of our current telescopes. The very definition of a star, a ball of plasma burning with fusion, would be shattered. The universe would reveal itself as a place where the familiar is merely one terrifying possibility among many. If dark stars are the universe's most profound secret, then how do we hunt for a ghost? How do we find something that refuses to shine, that barely interacts, that leaves almost no footprint beyond its crushing gravitational presence? This isn't like spotting a supernova. This is cosmic detective work on a scale that pushes the very limits of human ingenuity and our most advanced instruments. The first clue lies in their signature of annihilation. While dark stars don't emit light from fusion, the WIMP annihilation process in their cores does produce energetic particles, gamma rays, neutrinos, and positrons. These are the ghostly whispers of a dying dark matter particle. Our orbiting gamma ray telescopes, like Fermi, constantly scan the skies for these high-energy photons. If a dark star is lurking, its core would be a subtle, persistent source of gamma ray emission, distinct from the violent bursts of pulsars or black hole jets. It would be a faint, steady glow in the gamma ray sky, a cosmic fingerprint of invisible annihilation. Next, consider their colossal size and chilling temperature. A dark star, hundreds or thousands of times the sun's diameter, but only a few thousand degrees Kelvin, would radiate primarily in the infrared. This is where the James Webb Space Telescope, with its unparalleled infrared vision, becomes our ultimate cosmic bloodhound. Webb can peer through the dust and gas that obscures visible light, revealing faint, cool objects that were previously invisible. If dark stars are out there, Webb might detect them as diffuse, extended yet strangely cool sources in the distant early universe, or even as anomalous infrared blobs within nearby galaxies. They wouldn't look like typical stars. They'd be cosmic enigmas, defying conventional classification. But the most compelling evidence might come from what they don't do and what they do influence. If dark stars were the first seeds of supermassive black holes, then we need to trace the evolutionary paths of these galactic monsters. Observing the growth rates of the earliest black holes using next-generation X-ray observatories could provide crucial data. If we find more evidence of overweight black holes in the infant cosmos, it strengthens the case for a rapid dark star-fueled formation mechanism. Furthermore, these massive, cool objects would have a distinct gravitational influence. They would subtly perturb the orbits of nearby stars and gas clouds, leaving gravitational ripples that precise astrometry missions like Gaia might eventually detect. Imagine a faint, almost imperceptible wobble in the dance of stars at a galaxy's edge, caused by an unseen, colossal presence. The hunt for dark stars is a testament to humanity's relentless curiosity. It's a quest that forces us to question our most fundamental definitions, to push the boundaries of observation, and to embrace the terrifying possibility that the universe's most powerful engines might be silent, cold, and utterly invisible to the naked eye. We are looking for the ultimate cosmic illusionists, and every new piece of data, every refined theoretical model, brings us closer to unmasking them. We began this journey with the familiar blazing heart of our sun, a cosmic anchor, a definition, but the universe, in its infinite, brutal ingenuity, shatters those definitions. The theoretical dark matter star forces us to confront a chilling truth. The cosmos is far stranger, far more complex, and infinitely more unsettling than our limited senses allow us to perceive. These aren't just hypothetical objects. They are a profound challenge to our understanding of cosmic fire, galactic evolution, and the very nature of existence. They redefine what a star can be, twisting the comforting image of a nuclear furnace into a silent, annihilating shadow. They whisper of a universe where the most powerful forces operate in complete invisibility, shaping destinies from the shadows. If dark stars existed, if they still exist, then the universe's most dramatic acts of creation were often performed in the deepest, coldest dark, and the structures that define our reality, the galaxies, the supermassive black holes, might owe their very existence to these silent, annihilating giants. It's a universe built not just on light, but on the chilling, unseen power of cosmic annihilation, a universe where our very origins are entangled with the phantom dance of dark matter. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.